Welcome to the third lecture from chapter number 7. We are studying VLSI design and we'll continue studying CMOS NOT. And in the last two lectures, 7.1 and 7.2, we have studied CMOS NOT and we have studied its voltage transfer characteristics, and we studied different voltages respect to, for example, V output high, V output low, V input high, V input low, and noise margins, and we also studied VM, the middle voltage. And in this lecture we are going to derive a mathematical expression for the middle voltage. In our last lecture we studied that VM is the voltage on the VTC, where on the VTC curve VM is the voltage where V in and V out are equal, or is corresponding, or it's actually the intersection of M is equal to one line and this curve, the VTC curve. Right. So how would you draw this? How would you calculate a mathematical expression for VM? This is a schematic for CMOS NOT, and these are the two expressions that we have brought in from the course EDC, electronic devices and circuits. And we studied that since all FETs are voltage controlled devices, therefore this IDN and IDP, they must be dependent on the gate to source, the input voltage, because they are voltage controlled devices. And these are two nonlinear expressions, the simplest possible nonlinear expressions for IDN and IDP on the basis of the input voltage, gate to source voltage, or source to gate voltage, right? And for these two expressions we have these threshold voltages that we already know, the threshold voltages for N and P, and we have two new terms here, beta N and beta P, where beta N and beta P are device transconductance, and they are dependent on beta N is kappa N aspect ratio of N, where beta P is kappa N kappa P aspect ratio of P, where kappa N and kappa P are process transconductance, and they are not in the control of a VLSI designer. Process transconductance. So for the VLSI design, as a VLSI designer, only the aspect ratios are in your control. And in the next lecture we'll study more about aspect ratios and how can we control aspect ratios to obtain our desired characteristics for different Boolean expressions implemented using CMOS. So for now we won't discuss aspect ratios, right, but we will discuss them in the upcoming lectures, right? So aspect ratios will be discussed next. For the sake of this lecture we are going to derive an expression for VM, and this is our starting point from the last course, EDC, electronic devices and circuits. And right, so when we have VM applied as input, the same VM is available at the output. So if we have, for this circuit, if we have VM applied as input, we'll have the same VM available at output, right? And for this VM, we know that if we apply VM, let's check whether PMOS transistor MP is on or MN is on. So let's check. When we apply Vn is equal to Vp, Vn is equal to Vm, that is somewhere in the middle of VDD. Maybe it can be 2 volts, maybe 2.5 volts, maybe 3 volts if we are working with VDD is equal to 5 volts. Maybe this is 0.5 VDD, or this is 0.4 VDD, 0.45 VDD, somewhere in the middle, around the middle of VDD. So if we have Vm that is somewhere in the middle of VDD, around VDD by 2, so what would be VGSP? Let's check whether this PMOS is on or it is not on. VGSP is VDD minus VM. So since VM is around VDD by 2, this is VDD. So if we subtract these values, VDD minus something around VDD by 2, of course we are going to have a value that is greater than VDP, turning it on. Because we have already studied that for a PMOS is on if VGSP is greater than or equal to VTP, and it is equal to VTP in this setting, therefore it is on. What's about this is VSGP and this is VGSN, right? What is VGSN? VM minus 0. So VM minus 0, this is VM, and VM, of course, it is greater than VTN, and this is also on. So in the earlier scenario we studied that once we have this V in is equal to 0 volts, only PMOS was on. When we have this V in is equal to VDD, this NMOS was on. But in this setting where we have V in is equal to a middle voltage VM, we have both transistors VSG and we have both transistors MP and MN on. For that, they both will be conducting, and since they are connected in series, so the same current ID would be flowing through both transistors. So IDN would be IDP. So but what is IDN IDP when we have IDN would be IDP, but what is IDN and what is IDP if we have V in equal to VM? This V in equal to VM, right? So let's rewrite these expressions. Beta n over 2 VGSN is VM minus VTN squared. What's about IDP? This is beta p by 2 VSGP is VDD minus VM minus VTP whole square. So now we have these two new values of new expressions for IDN and IDP that we should put equal to each other to find the value of VM. So the next is that we are going to put these two, 1 and 2, in this equation IDN equal to IDP to find the value of VM, the unknown. Right. So let's start. It's very simple. Let's put these two equal to each other. Right. So IDN is equal to IDN. Let's put IDN is equal to IDP. So IDN is beta n over 2 VM minus VTN squared is equal to beta p over 2 VDD minus VM minus VTP squared. So this 2 cancels with this 2, and we can take this beta p here, and if we compute square root on both sides, this is like this, and if we multiply this square root inside this is times VM minus beta n over beta p square root BTN. Right, so now we have together the VM terms on one side, this VM term on one side. So if we take this VM here, this becomes plus VM, and we have to take this minus term on the other side. So this becomes minus VTP plus beta n over beta p square root, and this becomes plus 1. So we have taken, actually I have done something very quickly. I have taken this VM on this side and this whole on the other side, and it becomes a plus. So taking VM common, this becomes plus 1 VM. So VM can be written as VDD minus VTP plus beta n over beta p, the square root of this ratio, times VTN divided by 1 plus square root of 1 plus beta n over beta p. So right, so this question is correct, and we have now derived an expression for VM to numerically compute VM. Right, so this VM can be somewhere in the middle of VDD. It can be exactly equal to VDD. It can be smaller than VDD by 2. It can be equal to VDD by 2. VM can be smaller than or equal to VDD by 2. So there are 3 options for this VM. If we numerically compute in a given numerical problem, VM has 3 options. Either it is equal to VDD by 2, or it is smaller than VDD by 2, or it is greater than VDD by 2. So if it is exactly equal to VDD by 2, we call that NOT or inverter as symmetrical NOT. So it's a symmetrical NOT if it comes out to be VDD by 2. And how would it be VDD by 2? In this given expression, one can very easily tell that when will this VM be equal to VDD by 2. How? If we put beta n is equal to beta p and VTN is equal to VTP. So in this scenario, if we put these two, beta n equal to VTP, beta n VTN is equal to VTP, this comes out to be VDD, maybe let's call it VT, minus VT plus, this is 1 because they are equal to each other, so the ratio is 1, plus VT divided by 1 plus beta n over beta p is 1, square root of 1 is a 1, so this cancels, so this comes out to be VDD by 2, a necessary condition for this symmetrical NOT. So every NOT is not symmetrical NOT only if we have these conditions fulfilled. Beta n is equal to beta p and VTN is equal to VTP, only then we can have this VM exactly in the middle of the characteristics, exactly in the middle of the characteristics, VDD by 2, and this is also VDD by 2, only in a setting where these two conditions are fulfilled. Right. In the next lecture, we are going to solve a numerical problem based on CMOS NOT and symmetrical CMOS NOT. Thank you.